So let's have a look into how the sound produced by the oscillation in the pipes. And we have pipe open at both ends. And that's how the particles, air particles, are oscillating in the pipe. But there are two graphs. One showing the displacement of the particles. Another one showing the difference between the air pressure in the pipe and atmosphere pressure outside. And as you can see, at the open ends, the pressure, we have pressure nodes. There is no difference in the pressure between the air pressure, atmosphere pressure, and pressure in the pipe at the open node.
Wait, is this then like blowing in and then stopping blowing?
You like blow in it,
And then when it
start to oscillate.
Wait, I don't
But when you're
understand.
blowing in it, it's only open at one end.
No,
You're covering one.
it can be
Understand why
flute.
they're like going
Flute
in and-
open at both ends. You blow not from the end of the
Blow from the
flute,
side.
from the side. So it still
So it
have
can have a
those.
hole on the side as well.
We will look into the when pipe close at one end. We will look
I don't understand why it's just going like in and out. Like
because there is here outside. You see both sides open.
Yeah.
What if you don't blow in it? What if you just like
Yeah,
have
nothing
it in the air or just like
If
tap
you
it?
don't blow, you don't create the sound.
No, but what if you like tap it or something? Like bang it?
Yeah, you can create sound.
And it
yeah.
did the same.
So
Why are the
depends.
particles going like that though? I don't know.
Because here is outside there is atmosphere pressure.
Yes.
And at the ends, where it's open, pressure always will be equal atmosphere. You need to blow like really hard to change atmosphere pressure, which created by the kilometers of the height of the Earth atmosphere.
Yeah.
So pressure here is, but inside the pipe, due to the oscillations, the pressure can be higher than atmosphere pressure, all over. And as you can see, the more in the middle, particles not moving. There is a node of the oscillation of the particle. The most of the motion of the particles happens at the open ends. But the air pressure equal, so there is zero difference between the pressure of the air at the open end of the pipe and atmosphere pressure. But in the middle, the changes of the pressure are the biggest. It either become bigger than an atmosphere and push particles aside. That's why I'm moving.
That's how
And
the
then
waves-
atmosphere pressure push them
Because that's
back.
how the waves affect the particles. But I thought if you're like blowing line, the particles like are leaving the.
Yeah, they're not leaving the pipe because atmosphere pressure which push them back.
When is the pressure negative when it goes under the ground?
Negative pressure, it's not negative pressure because it's a difference between pressure in the pipe and the atmosphere pressure.
So it's
So
when it's
it's
less than that atmosphere.
Less than atmosphere. When particles
When it
are
pushes
spread
back.
out,
I understand
the pressure becomes less than
That's not a
atmosphere.
standing wave. That's like the other one.
It is a standing wave.
But
It
like,
is a
there's, like,
standing,
this,
but
though.
it is longitudinal wave.
Yeah, that.
Because the oscillation in the longitudinal wave, oscillation of the particle happens in the same direction as the wave propagates. Wave moving this way and particle oscillate the same way. That's a longitudinal wave. But as you can see, if you look on the pressure, you see that it will be the same diagram as we have with the string fixed at both ends. Now let's, if you will close pipe at one end, one side, only one side open. It will behave like what? Like string
Fixed on one point.
fixed at one end. Because now we have that here where pipe is closed, there is no motion of the particles.
If you had like if you had a speaker and you had like a string like tied onto the speaker, and it was just like loose. Would the string go like this?
Right.
Yes, string will vibrate, yes, of course, because how the loudspeaker works.
Vibration.
Vibration, there is a cone, paper cone, that's vibrate forward, backwards, creating that sound that's moving from the loudspeaker. How this membrane is moving, that when we will learn in Unit 3, learning about the magnetic forces in magnetic field, and there is a coil with a current, and there is a magnet, and when current through the coil changes, the force acting on the coil changes and coil vibrate forward, backwards. And that paper cone attached to the coil, and it will vibrate with the coil.
What if both ends are closed?
Both ends are closed. We're not looking into this situation. It's not part of the curriculum, but that's what will be the picture.
It looks like one because we're doing. Oh, but it's the opposite as the first one.
It is opposite to what it was with the pipe open at both ends. But this is not of the part of the curriculum.
Yeah.
So, as we already had formulas for string closed at both ends. So string fixed at both ends. And we have that longest standing wave that could exist in that string is like this, with the wavelengths equal double length of the string, and all other wavelengths, when standing wave can be created, equal to L divided by N, where N is natural number. 1, 2, 3, da 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 da. And we have the same picture with the behavior of the pressure in the pipe. Close it also. And pipe open at both ends. At both ends. We have, but now that will be not oscillation of the spring, there is a variation of the pressure. And so we will have, but you have same formula for the wavelengths. The longest standing wave of the variations of the pressure that can exist in this pipe is 2L, and all others 2L over N. And the frequency that
Is that
associated.
for the pressure? Is that for the pressure?
Yep, pressure variations. And frequency associated with the longest wavelength is the lowest frequency of first harmonic or fundamental frequency, which is V over wavelengths. And all other harmonics, we have Fn, frequency of the nth harmonic equals n times fundamental frequency. And exactly the same formulas apply to the pipe open at both ends. So for example, flute. So that's R. What
Is a saxophone one end?
saxophone is one end, yes. Because when you blow in it, you close other end.
Yeah.
So saxophone open at one end, flute at two ends. So that's why they make very different sound, because they have different. We'll look now into the possible standing waves when pipe open at one end.
What about a piano? Is that a string on both ends?
It's string. Piano has strings. You have a
Piano's-
hammer.
yeah, but it's
It's
like-
a hammer that hits strings, and they fix at both lengths. And what the difference between strings and piano?
They're like
Um, They're in a box.
Yeah, but they are different. On guitar, how are you changing the sound?
You like
You,
You control.
you're moving your fingers, you make it changing the length of the string. And so you're changing the
Oh, piano, they have
frequencies.
different lengths.
they're constant.
Piano, not they have
don't
different
change.
lengths, but they also have different thickness.
Oh.
They have different speed. They,
What
if
is
you look
thickness?
inside the piano, the strings, they're not all the same
What
thickness.
is the
Oh, but that makes sense because a guitar, like the last two ones are.
They're different thickness as well.
Yeah.
And what changed when we change thickness of this string? What it
The
changed?
sound.
So which characteristic it changed?
Oh, the hertz.
pitch.
The hertz.
Okay.
Or the
The speed?
decibels.
Speed. Yes, it will change the speed with which way will move in the string.
Why?
And as a result of changing the speed, it will change the
Frequency.
Why does the
frequency.
thickness change the speed? I just guess.
why it's changed.
Because think about it like this: if you have like a slingshot
What does?
and you
Shark
have
Tank
like
is like 8 hours without
one
it.
slingshot with
Yeah,
a thinner elastic,
Yeah. Like
What
then
the-
you're
the
gonna
guy-
go
For one episode.
not
Yeah,
as
the
further
people then
because
just
the elastic doesn't have as much
scream
power.
at the-
But
But
that's
if the
elastic.
elastic is like thicker, you're gonna go further.
Yeah, because it depends how high is it will be tension in the string. How hard the thickest string will have more power
Yeah, it won't be
moving
able
it back.
to provide as much tension.
So, changing the thickness of the string, change the speed of the wave in that string, and so changing its resonating frequency. Now, we had that for string fixed at one end, and the same will be for pipe open at one end. And we have that the fundamental, the longest wavelength was equal 4L, and all other with the higher harmonics that could form stained waves were 4L on N, but the N was only odd number, 1, 3, 5, 7, da 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 da. And only frequencies, again we have frequency and harmonic, equal n times fundamental frequency. But it's only odd harmonic exists in that case. So same will be with the pipes open at one end. It produces only odd harmonics. In all other standing wave cannot form. The waves,
Can you replace the n with 2n minus 1?
yes, we can use 2n minus 1 to represent odd number. Yes. Okay, that's pretty much all theory of how the sound is created in the pipes or wind instruments, and now we'll do some practice questions.